The content of this video can be found on pages 41 through 47 of your textbook, and it's meant to help you achieve learning objective number 10, which is to explain what is meant by the statement, "The atmosphere is heated from the ground up." If you've not already done so, it's a good idea to skim pages 41 through 47 before you watch the rest of this video, and pay particular attention to the bold words and to the figures and their captions. Please plan to read the content more thoroughly before you attempt the online vocabulary quiz or the concept quiz for this chapter. Remember from the last two presentations that Earth receives shortwave radiation from the sun and emits long-wave radiation to space. Understanding how the atmosphere is heated requires an understanding of how atmospheric gases interact with the short wavelength incoming solar radiation and with the long wavelength outgoing radiation emitted by the Earth. This diagram is very similar to figure 2.12 in your textbook, and it shows the effectiveness of selected atmospheric gases in absorbing incoming shortwave radiation. So in this diagram, I want you to notice that the shortwave radiation, solar radiation, is over on this side of the line. Okay, so from the middle of the graph to the left. And that includes the visible light that we see as with our own eyes, and ultraviolet and super high shortwave radiation, which is dangerous to us. So the atmosphere does a good job of protecting us from those things. So to a large extent, that comes from oxygen, free oxygen and ozone in the atmosphere. But it also shows the effectiveness of atmospheric gases in absorbing outgoing long-wave radiation, which is everything here on the right side. The blue areas represent the percentage of radiation absorbed by the various gases. The atmosphere as a whole is transparent to solar radiation between 0.3 and 0.7 micrometers. That includes the visible band of light. So most solar radiation falls in that range, and that explains why a large amount of solar radiation penetrates the atmosphere and reaches the Earth's surface. Also notice, though, that long-wave infrared radiation in the zone between 8 and 12 micrometers, right in here, can escape the atmosphere easily. That zone is called the atmospheric window. And for our purposes, it's important to remember that this is a window, and it's an escape window for long wave radiation. Notice that nitrogen, which is the most abundant constituent in the atmosphere, 78%, is a relatively poor absorber of incoming solar radiation. So we don't see much blue in the nitrogen graph at all. The only significant absorbers of incoming solar radiation are the water vapor, the oxygen, and the ozone. And that accounts for most of the solar energy absorbed directly in the atmosphere. So it's just water vapor, oxygen, and ozone that are absorbing the solar radiation. Oxygen and ozone are efficient absorbers of high-energy shortwave radiation. Oxygen removes most of the shorter wavelength UV radiation high in the atmosphere, and ozone absorbs UV rays in the stratosphere between 10 and 50 kilometers, that's 6 to 30 miles, without removing most of the UV radiation. Human life would not be possible because UV energy disrupts our genetic code. At the bottom of the figure, you can see that for the atmosphere as a whole, None of the gases are effective absorbers of visible radiation, that is radiation with wavelengths between 0.3 and 0.7 micrometers, right in that range. The visible light band constitutes about 43% of the energy radiated by the sun. Because the atmosphere is a poor absorber of visible radiation, most of that energy is transmitted to the Earth's surface. Thus, we say that the atmosphere is nearly transparent to incoming solar radiation, and that direct solar radiation is not an effective heater for the Earth's atmosphere. The atmosphere is generally a relatively efficient absorber of long-wave radiation emitted by Earth. Water vapor and carbon dioxide are the principal absorbing gases, with water vapor absorbing about 60% of the radiation emitted by the Earth's surface. Therefore, water vapor, more than any other gas, accounts for the warm temperatures of the lower troposphere, where it's mostly found. Although the atmosphere is an effective absorber of radiation emitted by the Earth's surface, it's nevertheless quite transparent to the band of radiation between 8 and 12 micrometers. Notice in the figure that the gases in the atmosphere, nitrogen, CO2, and water vapor, absorb minimal energy in those wavelengths. Because the atmosphere is transparent to the radiation between 8 and 12 micrometers, much as window glass is transparent to visible light. Although other atmospheric windows exist, the one located between 8 and 12 micrometers is the most significant one because it's located where Earth's radiation is most intense. By contrast, clouds that are composed of tiny liquid droplets are excellent absorbers of the energy in the atmospheric window. Clouds absorb outgoing long-wave radiation and radiate much of that energy back to the Earth's surface. Clouds then serve a purpose similar to window blinds because they effectively block the atmospheric window and lower the rate at which Earth's surface cools. This explains why nighttime temperatures remain higher on cloudy nights than on clear nights. We addressed that in some of our initial discussion, first day conversation that came to light. Because the atmosphere is largely transparent to solar radiation, but more absorptive of long-wave radiation emitted by the Earth, the atmosphere is heated from the ground up. I'm going to restate that. Because the atmosphere is largely transparent to solar radiation, lets it all through, but absorbs long-wave radiation that emitted by the Earth, the atmosphere is heated from the ground up. And this explains the general drop in temperature with increased altitude in the troposphere. The higher you get in the troposphere, the further away you get from the long-wave radiation associated with the Earth's surface. On average, the temperature drops 6.5 degrees C for each kilometer. That's 3.5 degrees Fahrenheit per 1,000 feet. That rate, 6.5 C per kilometer, or 3.5 F per 1,000 feet, is known as the normal lapse rate. Okay, so if you think back to previous presentations, we've already talked about lapse rates. That's how we can effectively expect temperature to decrease in the atmosphere. The fact that the atmosphere doesn't acquire the bulk of its energy directly from the sun is of utmost importance to the dynamics of Earth's weather machine. Near the surface, in an atmosphere with little or no greenhouse gas, the Earth's surface would constantly emit infrared radiation upward, both during the day and at night. Incoming energy from the sun would equal outgoing energy from the surface, but the surface would receive virtually no infrared radiation from its lower atmosphere. So if you don't have greenhouse gases, there's no atmospheric greenhouse effect. The Earth's surface air temperature in this case would be quite low. And small amounts of water on the planet would be in the form of ice. So in an atmosphere with greenhouse gases, the cartoon on the right side here, the Earth's surface not only receives energy from the sun, but also long-wave infrared energy from the atmosphere. So long wave. Incoming energy still equals the amount of outgoing energy, but the added infrared energy from the greenhouse gases raises the average Earth surface temperature to a more habitable level. Research of airless planetary bodies like the moon leads scientists to determine that if Earth had no atmosphere, it would have an average surface temperature well below freezing. Fortunately, Earth's atmosphere traps some of the outgoing radiation, which makes our planet habitable. The extremely important role that the atmosphere plays in heating the Earth's surface is known as the greenhouse effect. As discussed earlier, cloudless air is largely transparent to incoming shortwave solar radiation, and hence transmits much of it to Earth's surface, where it can be absorbed and then eventually re-radiated skyward. Two atmospheric gases in particular, water vapor and carbon dioxide, are meteorologically important because they absorb a significant portion of the long-wave radiation emitted by Earth's surface. As Earth's radiation heats, these absorptive gases, the temperature of the atmosphere increases. The atmosphere, in turn, radiates some of this energy out to space, but more importantly, it radiates an equivalent amount back towards Earth's surface. So without that complicated interaction, Earth's average temperature would be minus 18 C, right? Rather than its current temperature of about 15 degrees C, 59 degrees Fahrenheit. As a result, water vapor and carbon dioxide, which make Earth habitable for humans and other life forms, are called greenhouse gases. The term greenhouse comes because greenhouses are heated in a similar manner. The glass in a greenhouse allows shortwave solar radiation to enter and be absorbed by the objects inside. Those objects in turn radiate energy, but at very long wavelengths, to which the glass is an obstacle. The heat, therefore, is trapped in the greenhouse. And although the analogy is widely used, it's been shown that air inside greenhouses attains higher temperatures than outside air, in part due to the restricted exchange of warmer air inside and cooler air outside. Nevertheless, the term greenhouse effect is still used to describe atmospheric heating. Media reports frequently and erroneously identify the greenhouse effect as some sort of a villain in the global warming problem. However, the greenhouse effect and global warming are different concepts. Without the greenhouse effect, Earth would be uninhabitable. So I challenge you to think of the greenhouse effect as a very good thing, right? No matter what you think of global warming, the greenhouse effect is crucial. Scientists have mounting evidence that human activities, especially the release of carbon dioxide, are responsible for rising global temperatures. Thus, humans are compounding the effects of an otherwise natural process. So we're adding to the effect of the normal greenhouse effect. It's incorrect to equate the greenhouse phenomenon, which makes life possible with global warming, which involves undesirable changes to our atmosphere, caused mostly by human activity. The solar energy that isn't reflected or absorbed warms the Earth's surface. So in this model, a plot of solid Earth, the ground, where trees and other tall vegetation are sparse. And the ground in turn heats the lower atmosphere through the process of conduction. Convection and infrared radiation also play a part. The atmosphere also obtains latent heat from the processes of condensation as clouds form in convective storms. So this diagram, I don't think is overly complex, but it's a good one to sort of try to draw on your own, in your own notebook, and study this as you get ready for the exam. Air in the lower atmosphere is heated from the ground upward. We can see this is an area of conduction, but we also see escaping long wave radiation. And further warming occurs during condensation as latent heat is given up to the air inside the cloud. This diagram comes from the IPCC. It's a branch of the United Nations. It's intended to show the relative influence of greenhouse gases, ozone pollutants, aerosols, and albedo changes on the Earth's heat budget. It also shows how the combined effects of those human-caused emissions compare with the effects of variation in solar radiation. Since 1750, humans appear to have caused an annual surplus of about 1.6 watts per square meter in the Earth's heat budget. Variations in sunlight intensity from sunspots and things like that only really accounts for 0.12 watts per square meter of the extra surplus. So yes, solar storms, sunspots are having an influence on a 10 to 11 year cycle on our temperature, but not as much as the greenhouse gases have been warming. So that means only about 8% of the total warming is likely to have come from the result of the sunspots, the solar output. Most anthropogenic sources of change fall within the long-lived greenhouse gases and ozone category up here at the top. Is there real evidence that the composition of the atmosphere has been changing over the last 60 years? Yes, there absolutely is that evidence, especially with regard to carbon dioxide. Measurements recorded at NOAA's Mauna Loa Observatory document an increase of 82 parts per billion in the atmospheric CO2 concentration since 1958. Currently, the concentration of CO2 in the atmosphere is in excess of 392 parts per billion. Other greenhouse gases like methane and nitrous oxide are also on the rise. It's highly likely that human emissions have contributed to the increased levels of greenhouse gases in the atmosphere. Higher amounts of CO2 can reasonably be expected to result in more absorption of long-wave radiation in the 2 and 4 to 5 micrometer wavelengths. So those are typical of long-wave radiation. And that's why we expect an increase in temperature as a result of increased CO2. Use the content provided on the Canvas site as well as outside internet sources to verify that you can formulate answers to these questions. If you can comfortably answer those questions, you're in great shape. If you can't, review the textbook, rewatch the video, and see if your abilities improve. If you're still completely stumped, start a discussion on the Canvas site or ask me for help.